Okay, unit cells and basic structures. So X-ray crystallography can help us to determine how the atoms or molecules are arranged. That's the crystalline lattice, the regular arrangement. The particles are going to arrange themselves in a particular lattice to minimize their energy. Energy is the driving force for a lot of things. And so they're going to come together and arrange themselves in a way that gives them the lowest potential energy. So we're going to look at several different ways that these particles can arrange themselves. And so we look at a unit cell. That's the smallest divisible unit of a crystal. When you repeat it in 3 dimensions, it reproduces the whole crystal. So here's a representation 2-dimensionally of a crystal lattice. And here is the smallest piece that if we copy this over and over again, we're going to get the whole lattice pattern. The circles represent lattice points. Those would be occupied by atoms, ions, or molecules. So the dark square here is the unit cell, and then the lighter ones show how it repeats and forms the lattice. Everybody okay with that? That's what we mean by a unit cell. So we're going to look mostly at cubic unit cells. These are variations of a cube with 8 corners, 6 sides. And these all have names. We're not going to worry about these names, but some of you may go on into engineering or geology, and these things will become more important. In a cubic cell, the lengths of the sides are all equal, and the angles are all 90 degrees. That's a cube. A tetragonal would be a tetragon, and so now the lengths of the sides are different, but the angles are still 90 degrees. You can have orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic, and so these are all these different shapes. We're going to be looking at cubic cells. We're going to look at structures where we just have one kind of atom, just to make it more simple. Some of the pictures are going to have different colors. Those different colors do not represent different kinds of atoms. They're just to aid the visualization. So we look at a coordination number. The coordination number is the number of atoms with which each atom is in direct contact. Direct contact is important because that's the strong interaction between atoms. We also look at the packing efficiency. How much of the volume is actually occupied by the particles themselves? If you have a high coordination number, you'll have a greater packing efficiency. So here are 3 of those cubic cells. And we'll talk about each of them in more detail, but this is sort of a summary. There's a simple cubic, there's body-centered cubic, and face-centered cubic. And they're going to be different in their coordination numbers and their packing efficiencies, but as the coordination number increases, packing efficiency increases. So first is the simple cubic unit cell. So here we have an atom at each corner of a cube. This is the unit cell. It goes from the center of this atom to the center of that atom. And if we take this and reproduce it, it will fill out those atoms. So here we have an atom, and the atom has a radius. And we can figure out how long the side of this cube is because it's the radius of one atom and the radius of another atom. And so the length here is equal to 2 times the radius of whatever particle this is. And then you could calculate the volume based on that as well. We also want to look at how many atoms are in this cell. So there's parts of 8 atoms in here, right? But none of them are whole. So this is 1/8 of an atom, and that's 1/8, and that's 1/8, and this is 1/8. You get the idea. So overall, there's one atom in this unit cell. But the way the unit cell is drawn, so that we can see how they're connected, we've got 8/8 of atoms. There's different ways of looking at it. So this is the picture we were just looking at. Here is looking at that with full atoms. And here is looking at the coordination number. So here's the one unit cell. And then we're looking at this atom on the corner to see how many atoms does it have direct contact with. And it contacts 1, 2, 3, 4, 5, 6. So it's in direct contact with 6 atoms. So the coordination number is 6. The packing efficiency is 52%. That can be calculated by calculating the volume of one atom and the volume of the cell. And it's the part over the whole times 100. So 52% of this is occupied by atom and 48% is empty space. So here's a two-dimensional problem. Calculate the packing efficiency of the two-dimensional lattice shown here. They don't give us any numbers because we don't actually need any numbers. So packing efficiency, I'm just going to call it PE, is going to equal, this is two-dimensional, so we're going to look at area, right? It's the area of the atom divided by the area of the unit cell times 100. Part over the whole times 100. So here's our unit cell. We're going to need a variable. Let's use R for the radius of a cell, radius of the atom. So we're going to say R equals the radius of the atom. So here we've got a circle. What's the area of a circle? Pi r squared. Okay, so that's the area of the atom. And then we've got the unit cell, and this is R, and this is R. So each side is 2R, and what's the area of a square? It's the length times the width, or L squared, right? So that's going to be 2R, the quantity squared, which is 4R squared. So packing efficiency, the area of the atom, pi r squared, divided by the area of the cell, 4r squared, times 100. The r's cancel out. We didn't need to know what the radius is. It doesn't matter. The packing efficiency is the same. So this is equal to pi over 4 times 100. This is chemistry, not math. We actually do the math. So I'm going to use the pi button on my calculator. Divided by 4 times 100. My calculator says 25 pi. That's not what I want. There we go. 78 point, a whole bunch of things. Call it 78.5%. Any questions? Yes?
According to the diagram in slides previous, it says the packing efficiency is at 6%. How could it be higher?
So that's a good question. The 52% is looking at a three-dimensional lattice. Here we're just looking at the two-dimensional, and so it's different. Yeah. Because in the third dimension, you also have empty space, and so the percentage is going to be.
Is the white box there?
Yeah, we're looking at the white box. Mm-hmm.
So in there, there's one atom, or is there touching 4 atoms?
The coordination number here would be 4. You can't really compare two-dimensional and three-dimensional. What would the volume of an atom be? 4/3 pi r cubed, right? 4/3 pi r cubed. And then the volume of that unit cell, it's 2r on a side, so it'd be 2r cubed, right? So that would be 2 times 2 times 2, 8. 8r cubed, and 4/3 pi r cubed, and the r cubed cancels out. So we've got 4 divided by 3 times pi divided by 8 times 100. 52.4%. Which they call 52. So you can do it in 2 dimensions, you can do it in 3 dimensions. Any other questions? That was the simple cubic. The body-centered cubic unit cell has 1 atom in the center and 1 atom at each corner of the cube. So this is where we've got different colors. This atom in the middle is the same as the atoms at the corners. We're just using a different color so that we can see it. Otherwise, it turns into this big mess of purple. The atoms in the sides now, on the corners, aren't actually touching along the sides anymore because of this atom in the middle. And so we can't just say the length of the side is 2r. It's a little more complicated. We have to look at, well, where are these atoms touching? They're touching on the diagonal from one corner to the opposite corner of the cube. So that's C. So C would equal 1, 2, 3, 4 R's, 4 radii. And then we're doing some geometry here. You can figure out what B is, and you've got a right angle. And so L squared plus B squared equals C squared, Pythagorean theorem. You go through all of that and you solve it and you get this. L is equal to 4r over the square root of 3, right? I don't expect you to remember that. So there's what we were looking at. Now we still have 1/8 of an atom at each of the 8 corners plus a whole atom in the middle, so this has 2 atoms in the cell. Here we're looking at all intact atoms, and then here we're looking at the coordination number. This is beginning to get a little more difficult to look at. The coordination number here is 8. And you can calculate the packing efficiency much like we just did, and here it's 68%. So it's gone up from 52 to 68. An atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What's the volume of the unit cell in cubic centimeters? We're going to need L equals 4r over the square root of 3. L equals 4r over the square root of 3. So what's r? It's the radius. What's the value of it? 138 picometers, right? And we're supposed to find the volume in cubic centimeters. I don't know about you, but I prefer to convert units when they're not cubed. We're going to end up cubing this, and so I choose to convert this to centimeters before we stick it into stuff. So converting from picometers to centimeters, we have two metric prefixes, so it's best to do this in two steps. So first we're going to convert to meters, and then we're going to convert to centimeters. So centi means 10 to the minus 2, and pico means 10 to the minus 12. It's great to be able to do that in your head, but always check it with your calculator. (1.38 times 10 to the minus 8). Centimeters. This is the length of a side. What's the volume of the cube? That cubed, right? So the volume of this is equal to L cubed, which is 4R over the square root of 3 cubed. So 4 times R, 1.38 times 10 to the minus 4, 10 to the minus 8. I don't know where that came from. Centimeters divided by the square root of 3, that quantity cubed. So 4 times 1.38 EE minus 8 divided by the square root of 3. And then that's going to be raised to the third power. I'm getting 4.69 times 10 to the 24th. Something's wrong. Oh, I divided instead of multiplying. 4 times 1.38. That'll be better. There we go. 3.24 times 10 to the minus 23rd. That sounds better. Cubic centimeters. I expect this to be a very small volume, right? Because we're looking at an atom, too small to see, 138 picometers. My first result was this ginormous number, so I knew immediately that I had done something wrong. And I divided instead of multiplying, so. Any questions? Face-centered cubic. Now we have atoms along the faces. So here's an atom along this face and that face and this face, and then we still have those atoms in the corners. So we have one atom from all of the purple ones in the corner, 8/8, and then each of these gold ones is half of an atom, right? So there's half here and half there, that's 2, and then there's, I'm sorry, that's half and half is 1. I am such a dork. There's one atom here, and then one atom over there, and another atom over there. So here we have a total of 4 atoms in here. The geometry is a little easier, finding out the length of the side here. They're touching along this diagonal here, so this segment B is equal to 4R, and this is L, and that's L, and you can calculate it, and you end up with L equals 2 times the square root of 2 times R. Yes?
Are all the purple shapes on the top equivalent to 1 atom?
The purple shapes are each 1/8 of an atom, And so the ones up here add up to half an atom, and the ones down here add up to half an atom.
How do you get 8 then? It's not just 6 orange ones?
There's 6 yellow ones, but they're half. So that's 3, plus 1 is 4. It's a little hard to see. So these purple ones at the corner, 1/8 of an atom at each of the 8 corners, so that's 1 atom. And then the face-centered ones are each half of an atom, 6 faces, so that's 3 atoms. And then you look in here, and good luck counting those. I'm just going to believe them. The coordination number is 12. Packing efficiency is 74%. Here's another problem. Chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeters. This is one of those critical thinking problems. One of the things that's a little tricky about this problem is we just talked about a face-centered cubic unit cell, and so the first few times I taught this chapter, I started off with face-centered, the equation. It's body-centered. I don't know why they stuck it in here, maybe just to mess with us. So we need the length of the side. It was 4r over the square root of 3? Yeah, thank you. I don't remember those either, that's why I don't expect you to remember them. So if we know the length of the side, then we can calculate the volume, right? The volume is that cubed. Not there, over here, the whole thing cubed. It's asking us to find the density. So we need to think about, well, what is density again? Mass over volume. We can calculate the volume of a unit cell. How do we calculate the mass of it? How many atoms are in a body-centered cubic unit cell? 2. Could we find the mass of 2 chromium atoms? Sure we could. So we need 2 atoms. It's chromium, right? So we could go to moles, right? And then to grams. We got atoms down here. And moles up there. And grams up here and moles down there. Because the molar mass on the periodic table, 51.9961. That's the mass in grams of 1 mole of chromium atoms. We want the mass of 2 atoms. 1 mole is Avogadro's number of atoms. So atoms cancel, moles cancel, and we get mass in grams. Yeah? That's a good question. Where did I get the 2 from? I got the 2 because in this body-centered cubic unit cell, we've got an atom in the center, and then we have the ones at all the corners.
On the chart, it says the atoms per cell is 4 and face-centered.
But this is body-centered. Yeah. That messed me up too. Yeah. Face-centered is 4, and then we need to use a different L. But we could do that, but this one's body-centered. I think they were just trying to be mean. So 2 divided by 6.022 EE 23 times 51.9961. We'll go with 4 sig figs, 1.72 6, there's our 487, times 10 to the minus 22 grams. Should be small, mass of 2 atoms. Here we've got picometers. Again, I'd rather convert that before I cube it. We did that on the previous problem, so I'm pretty sure that's going to end up to be 1.25 times 10 to the minus 8 centimeters. So 4 times 1.25 times 10 to the minus 8 centimeters divided by the square root of 3, quantity cubed. That's our volume. .40 56 times 10 to the minus 23rd cubic centimeters. So I've got the mass, I've got the volume. The density is the mass divided by the volume. 1.72687 times 10 to the minus 22 grams divided by 2.4056 times 10 to the minus 23rd cubic centimeters. .1784. And I have 3 sig figs, grams per cubic centimeter, which would round to 7.18 grams per cubic centimeter. Hey Siri, what's the density of chromium?
The density of chromium is about 7.14 grams per cubic centimeter.
That's pretty close. Any questions? Another way to think about the crystal structures is to think about stacking the layers of atoms, or stacking the atoms in layers. What corresponds to the simple cubic cell is where you take a layer of atoms and then the next layer is stacked directly on top. So this atom in this layer is directly above the atom below. Now, if you play around with some marbles in a little box or oranges or something, that's not what they're going to naturally do, right? Because these are going to want to fall down into the divot caused by the others in the bottom layer. But the simple cubic cell, they are on top of each other. There's a lot of empty space in this structure. So you can cause the single layer to be more efficient by staggering the atoms. So this atom is not directly in line with the one next to it. This row is staggered so that they can nestle closer together. So this row is offset by half of an atom, and then this one lines up with the first, and this one's offset by half, and that one lines up. So then we can look at taking layers like that and stacking them. So we've got that layer A, so that's increased the efficiency. We can further increase the efficiency by when we take this second layer, by moving that over so that the blue atom is sitting in the little hole or the divot here caused by these 3 red atoms. Can you visualize that? this is what marbles or oranges or any spheres would naturally do when you try to cram them in a box. So we've got layer A and we've got layer B. Then we have a choice when we put the third layer on. The third layer could be directly in line with the first layer. So there's layer A, here's layer B, and the next layer is going to be the same as A. They're directly lining up. This is called hexagonal closest packing. This has an efficiency of 74%, a coordination number of 12. The unit cell here is hexagonal rather than cubic. It's hexagonal closest pack. Or that third layer, oh, never mind. Let's talk about this some more. I don't know what's coming next. So this would be the unit cell. And the angles here are 60 and 120. That's what makes it not cubic. If we look at this whole thing, we can see how it's a hexagon. And then there's cubic closest packing. Here, that third layer, instead of lining directly up with layer A, is also offset. And so we get an ABC pattern. This is called cubic closest packing because the unit cell here is cubic, and this is exactly the same as the face-centered cubic unit cell. It's just a different way of thinking about it. So here's our three layers. There's layer A, B, C, and then this would be A again. Put those together, tip them at an angle, cut them up, and you get the face-centered cubic.